Discuss about good morning. Today we will discuss about forced oscillations. When an oscillating system is driven by a periodic force that is external to the oscillating system, that is called as forced oscillations. Naturally, we know that due to the presence of dissipative forces such as friction, almost all the oscillations are damped. That is, the amplitude of the oscillations keep on decreasing. So, if we wish to sustain the oscillations, we can apply an external driving force. The most familiar example is a swing. When someone else is pushing the swing to maintain the oscillations, we can consider that as a forced oscillator. Now let's consider the different forces acting on a forced oscillator. By default, since it is an oscillator, there is a restoring force which is defined as minus k into x, where k is the force constant. Then, due to the presence of dissipative forces, we have the damping force, which can be defined as equal to minus gamma into velocity, where gamma is the damping coefficient. Then, since we are applying the external force, there is the presence of external driving force F equal to F0 into sin pt, where F0 is the amplitude and P is the angular frequency of the driving force. Therefore, the equation of motion of a forced harmonic oscillator can be written as mass into acceleration equal to the restoring force, damping force plus the external driving force. We can rewrite this equation as same as in the case of damped oscillator. We rewrite it again where 2c equal to gamma by m and omega 0 square equal to k by m, where omega 0 is its natural frequency and small f0 equal to f0 by m. Fine. Now, we can see that this is a linear non-homogeneous differential equation. We can, because of the presence of this x and t, it's a non-homogeneous equation whose solution is a sum of two terms, a complementary function and a particular function. Complementary function corresponds to the solution of this homogeneous part, which we have already obtained in the case of a damped oscillator, and now we have to obtain the particular function corresponding to this non-homogeneous part. To obtain the particular function, let's assume a solution of the form x equal to a sin pt minus theta, where a is the amplitude of the oscillator and theta is the phase difference between the driving force and the displacement of the oscillator. Now, differentiating this equation x, we get the expressions for velocity dx by dt and d square x by dt square. Now, substituting this dx by dt and d square x by dt square in our equation 2, here we get this expression d square x by dt square plus 2c into dx by dt plus omega 0 square into x equal to f0 sin pt. Now, rewriting this expression, we get this form. Fine, you can write it down. Now, equating the coefficients of sin pt minus theta, this term, and also the equating the coefficients of cos pt minus theta, we get A omega 0 square minus P square equal to F0 cos theta, and equating the coefficient of cos Pt minus theta, we get 2C AP equal to F0 into sin theta. Now squaring and adding these two equations, you will get this form, or just rewriting it again, we get the expression for the amplitude A as equation number 4. Now we substitute this expression for A in the solution for x. Thus we get x equal to, instead of A we have this term and sin Pt minus theta. This equation 5 is the particular function for the non-homogeneous part of the equation of a forced harmonic oscillator. From this expression, it is clear that it is an oscillatory function of frequency P. Now, we started by seeing that the solution of the forced oscillator has two terms, which is a complementary function and a particular function. The complementary function we have already obtained in the case of a damped oscillator, and here we obtain the particular function. So the total solution is x equal to A0 e raised to minus ct sin omega t plus phi, which is a solution of the damped oscillator, plus this particular function which we obtain now, A sin Pt minus theta, where A equal to this expression. Here, the first term on the right hand side represents the damped oscillator of frequency omega, which is the frequency omega with its amplitude decaying exponentially, as it is clear from this A0 e raised to minus ct, and it may decay to 0. And the second term corresponds to the driven oscillations of frequency P and having amplitude A. Now, to obtain the value of theta, we can divide these two expressions. If we divide this one by this equation, we get F0 into tan theta equal to 2CAP divided by A into omega 0 square minus P square, that is F0 tan theta equal to 2CP divided by omega 0 square minus P square, where A and A cancels. Thus we get theta equal to tan inverse 2CP divided by omega 0 square minus P square. And tomorrow we will see the different values or forms of this expression depending on the values of omega 0 and P. We know that omega 0 is the natural frequency of the oscillator and P is the frequency of that driving force.